Today we are going to look at a special kind of embeddings called Matryoshka embeddings. This is a new and interesting approach and can be used for different applications like retrieval augmented generation or just plain search engine. So in this video, I'll compare whether this embeddings approach is any better than just using principal component analysis to reduce the dimensions, or is training and using a specialized model built just for this is any better. So stick around and we'll find out. So basically, what Matryoshka actually means is a kind of a Russian doll. Here's the full picture of the doll. Inside every big doll, there will be a smaller one, and in turn, there will again be a smaller one, and so on. So the idea here with these Matryoshka embeddings is that it allows more flexibility when you are using the embeddings. So typically when you extract embeddings from a language model or a vision model, they give you a fixed size of embeddings, usually 768 dimensions or 1024 dimensions or whatever. And you have to use all of it. But this kind of embeddings, it allows you to truncate those embeddings or slice those embeddings into smaller sizes. So maybe you are resource constrained and you can't store the full embeddings because of huge dataset. You can use a portion of that embedding rather than storing the full embeddings. There are several models already built and trained that you can use using sentence transformers library. So one such kind of model is Nomic Embed Text version 1.5, and this model allows you to use several dimensions of the embeddings. So here, for example, the full embedding dimension is 768, but you can also truncate the embeddings and use the first 512 or first 128 or even 64 dimensions. So this is a relatively new approach about condensing the dimensions and using them for your retrieval or other kind of applications. So in this video, we'll briefly go through how these models are trained and how we can use them in our application. And I will also compare this approach with other dimension reduction techniques such as principal component analysis. Let's take a look at how these models are trained. So we have the input corpus and we ask the model to generate the embeddings. And using these embeddings, the model is trained in such a way that, so basically the objective is to minimize the distance of the embeddings that are from the same group and also maximize the distance between the embeddings from different groups. Now, in addition to using the full embeddings, the idea here is to use only the subset of the embeddings. So for example, if we had the embedding dimension of 768, we would only take, let's say, 64 dimension or the 256 dimensions rather than the full embedding matrix. And then using these first 64 or first 256, we train the model on the same objective of minimizing the distance of the embeddings from the same group and maximize the distance for embeddings from different groups. So what this basically does is forces the model to put more information in these slices so that later on, even though when we use the subset of this embedding, we can still be sure that all of the semantic information necessary are present in these slices as well. Let me show you the setup for this demo. So here I have a set of answers that I want to embed. So using the model, I generate the embeddings. I not only want to use the full embedding matrix, but also reduce the dimension of the embeddings. So there are a couple of ways that we will use. One is just by slicing the embeddings matrix. So we take the first 64 dimensions or first 128 dimensions. And the second approach is we'll use principal component analysis to reduce the dimensions. So here this embedding reducer 1 and 2 indicate these kind of approaches. And once we pass our full embedding matrix through this reducer step, we will get the embeddings with lower dimensions. And using these embeddings, we will create separate KNN index or the nearest neighbors index. And later on, we'll use all of these KNN index to evaluate our model performance. Let's look at the code now. I've imported some of the libraries that we will use later on. The first thing that we do here is load the dataset. So this dataset is a collection of question and answers from Stack Overflow. And for every question, there can be one or more relevant answers. And using DocDB, I just combine the dataset so that it's easier to process. So here I have joined the queries with the scores data frame so that I know that for every query, what is the expected answer IDs. So if we look at the data frame now, so we have the ID of the query, the text, and the relevant answer IDs. We'll use this later on when we want to evaluate our retrieval model. Now the next part is loading the model. As I showed before, there's this model called nomic embed text, and we can just use this sentence transformer class to easily load the model. And if you have GPU, it will also automatically load to the GPU. And then we take all of the answers from our answers data frame. And for this demo, I've only chosen to use the title field of the data frame and then extract the embeddings from the titles only. If we look at the shape of the embeddings that was generated, so we have around 32,000 answers and the embedding is 768 dimension vector. So this is the full embedding. Next, let's define a function that will give us nearest neighbors index based on the embeddings of the answers and also answer IDs. So here I'm using a library called EasyKNN, which allows us to build this nearest neighbors index quite easily. As I mentioned, we have a couple of approaches to reduce the dimension. The first one is just slicing the embeddings, which the Matryoshka embeddings allows us to do, right? So here this function basically accepts the embeddings and then just takes the first X number of dimensions and then returns it. And then there is also a closure defined there called transform. This will be used when we want to reduce the dimensions of the query as well. So here transform is a closure which takes a query vector and then returns the first n number of dimensions from this vector. Similarly, we have PCA based dimension reduction technique. So this reducer will basically train principal component analysis from scikit-learn, and then also it will define a transform closure which will use the same trained PCA and then transform it into the lower dimensional embeddings. Now that we have all of the building blocks ready, so let's use all of these techniques. As I mentioned before, the Matryoshka model allows us to truncate the embeddings in these dimensions. So here I have 4 set of embedding dimensions. And also, since we want to use principal component analysis as well, so I have defined a dictionary here with the slicing approach to reduce the dimensions and the PCA approach. And here as a baseline, we'll create an index based on the full embeddings. And I'll also store some of the metadata here, such as the size of the embeddings and also the time it took to build the index. Here in this code, we loop through all of the embedding dimensions that we want to reduce to. And basically for every dimension reduction technique we have, again, we loop through them. And the interesting thing here is we call the dimension reducer function and pass our full embeddings and then reduce the dimension. And this function also returns the transform function, which we will use later on when we are querying our index. So here I again store the metadata of the index, including the time it took and also the size of the embeddings. So this is all we need. And once we run this, we have all of the indexes and we're ready to use these indexes. This is how our retrieval step looks like. So we have a query, and then we again ask the model to generate the embeddings. This embedding again is a full set of embedding, right? And now we will pass this full embedding through our embedding reducer, be it slicing approach or using principal component analysis. And then we get the embeddings with reduced dimensions. And then using these reduced embeddings, we will search in our nearest neighbors index, which will in turn return the similar answers. And before we move forward, let's write a function to evaluate as well. So here, this function basically uses all of the queries that we have and then sends a request to the index. As shown here, the index has neighbors function which accepts a query vector. And then using our transform function that we defined, so we reduce the dimensions of this query vector as well. And from here, we retrieve top 10 most similar answers. And once we have the answer IDs, then we compute the recall using this formula here. And then finally, we return the average recall score and also the time it took to do all of this. And just to try it out, let's run this function on this embedding type, which is PCA 64. And this function will give an output like this, where the first output is the recall score and the second one is the time it took in seconds. So it took about 2 seconds and the recall score here is 0.34. And this is it. So we just call this evaluate function on all of the embedding types that we have. And let's see what the results look like. Now let's take a look at the memory uses of the embedding. We currently have about 32,000 answers that we have in our index. So when we use the full embedding dimensions, that is 768, it takes 94 megabytes of memory. But as we go down, the memory size decreases. For example, when we only have 64 dimensions, it only takes 8 megabytes of memory. So this is quite a lot of reduction in memory uses. But let's see what happens with the model performance. Before we look at the model performance, let's first look at the time it takes to create the index. So basically, when we have the full embeddings, that is 768 dimensions, it takes the longest. And when we use PCA, PCA takes a bit longer than the slicing approach. For PCA, it is understandable because it has to transform the embeddings from higher dimension to lower dimension and then give those lower dimensional embeddings to the index creation process. Whereas the slicing approach, where it's specified here as MAT-EMB. So this one is just a very simple operation where we just take the first 512 or first 256 dimensions from the full embedding matrix. When we look at the time it takes for the evaluation, we see that the PCA approach, where we reduce the embeddings using PCA, it takes the longest because once again, the PCA has to transform the data from higher dimension to lower dimension. So it adds extra matrix multiplication step in between. However, for the other approaches, such as using the slicing approach to reduce the dimension or even using the full embedding size, we see comparatively lower time for the evaluation to finish. So here the time measured is to run the evaluation for all 876 queries. So here it seems that the slicing approach, which takes 128 dimensions, is the most fastest, which is a bit interesting because there is also a 64 dimension index, but there it takes a bit longer than 128 dimensional index. Now finally, let's look at the model performance. Here I'm measuring recall at 10 for different embedding sizes. And interestingly, using PCA 256 dimensional embeddings has the best performance. So here we see the recall of 0.4 for PCA with 256 dimension compared to even using the full embedding dimensions, that is 768. Interestingly, using PCA to reduce the dimensions to 128 has almost the same performance as using the full embeddings. So this is very interesting. And one thing that puzzles me here is why PCA is performing much better than using the full embedding dimensions. Using the slicing approach to reduce the dimension also has very competitive performance. As we saw before, the time it takes for PCA to reduce the dimension adds additional overheads. So perhaps using the slicing approach to reduce the dimensions might make sense, even though the performance is slightly lower compared to PCA in almost all of the cases. And using the full embeddings here, at least for this dataset, does not really make sense because it takes a lot of memory. Second, this also has lower recall compared to using lower dimensional embeddings. So there's really no benefit of using the full embeddings here. Obviously, this will differ from dataset to dataset. and also the model that you use. But for this case, this is the result. So the interesting thing we saw earlier was the high performance of PCA to reduce the dimension, even when we were using the full set of embeddings, right? So here what this plot shows basically is the explained variance. So how PCA reduces dimensions is, so you specify the number of components that you want. So in this case, the embedding dimensions. So let's consider an example that I want to reduce the dimensions to 64. So how does PCA choose the component? In PCA, every component is in the order of their importance. So I'll define what importance actually means. When we are reducing the dimension, we are essentially losing some information. And during this process, we want to preserve as much information in the data as possible. And how PCA works is that it selects the components that explain the most variance in the data. So for example, if we look here, the first component explains about 3% of the variance in the overall data. So data here means the embeddings. And as we go up, so this is a cumulative curve. So we are adding, for every component, we're adding the explained variance ratio up to that component. So if we look at the explained variance ratio up to the 64th component, we see that these 64 components, they already capture 50% of the variance. And if we increase the number of components here, this green line is for up to 128 components. So using just 128 components explains 70% of the variance in the data, right? And similarly, when we have 256 components, it is already explaining 90% of the variance in the data. And lastly, when we take 512 components, this already explains 100% of the variance. So this means that after 512 component, even if we were to increase the number of components to, let's say, the original embedding size 768, this would not give us any more extra information. Basically, we can consider those components to be redundant. 512 components are already explaining 100% of the variance in the dataset. And I think this is why the PCA was better in terms of recall score that we saw earlier. And looking at this, it seems since 256 components already explain 90% of the variance, this seems to be a good number and a compromise between the dimension of the embeddings and also the quality of the reduced embeddings. So this is all I wanted to share today. I hope you found this video useful. Obviously, if you are trying, please compute the metrics on your own dataset and on your own models, and then find out whether or not you want to use PCA or some other dimensionality reduction techniques. Thanks for watching. See you next time.